Hello everyone, welcome to the lecture series on Fundamentals of Generative AI and Large Language Models. We are in the week 5. In the previous session, we had seen what are the limitations of variational autoencoders, and we have seen what is the key motivation for GAN, and towards the end of that particular session, we have also seen something called as what exactly is adversarial learning. We did not go in detail about the generator and discriminator. In this particular session, in today's session, we will look into GAN architecture, where we will look into in detail what exactly is a generator and what is a discriminator. So, this is a generator training. So, let us see what exactly it is, and what we are looking into now is, let us understand how a generator is trained in a GAN. Now, the process, let me first, okay, the process starts or the process begins with a random noise vector Z, and if you look into Z is having some dimension here. This means Z is a d-dimensional vector, and its values are usually sampled from an distribution, and that distribution here is a standard normal distribution. So, the very first step, generator is the one which has to generate the fake samples. From where it will generate the fake samples? It has to generate from some random noise, and that random noise is being sampled from a Gaussian distribution. That is what is the first step. Now, whatever is this random noise Z does not initially contain any meaningful information. It is simply a set of some random numbers. Okay, next, this random noise vector is passed as an input to a generator, and generator here is a neural network. Whenever you say a neural network will have certain parameters, and that parameter we are denoting it as phi, and here phi represents the trainable parameters of a generator. Now, for this generator, what is that we are passing? We are passing Z. So, when you pass Z, then generator will transform this low dimensional latent vector into a generated image. So, generator is the one which will take Z as an input, and then it is going to convert that into, it is going to transform this low dimensional random vector into a generated image. So, generated image here is denoted as this, which is nothing but X hat. Okay, I hope this bottom part is clear. Random noise, which is sampled from Gaussian distribution, is passed as an input to a generator. Generator is a neural network which will transform this noise into a generated image. Here the generated image is denoted as this G phi of Z, or it is also X hat. Right. Now, once we get this generated image, now this generated image has initially this can have any number of the dimension is not fixed here, but by the time you generate an image, this generated image has the same dimension as the real images in the training data set. So, the size should be same as the real image. Why is that we have to do? Because we are passing it to a discriminator, and discriminator will also see a real images. Therefore, generated image size should be same as the real images. For example, if the real image contains a grayscaled image, and if that image is of size 28 cross 28, then the generator also produces an image of size 28 cross 28. Suppose if a real image is a colored one, if the data set contains a color image which is having a size 64 cross 64 cross 3, then the generated image also will have the same size. Why? This is necessary because both real and generated image must be compatible with the same discriminator network, because discriminator is the one which will be seeing real image as well as generated image. If generated image size is very less, is it not discriminator can easily identify that this is an generated one? So, in order to avoid that, first motive here is generator has to generate an image and the size has to match with the discriminator. Okay. So far, let me once again revise to you, because this is very important architecture, and your entire week 6 is once again based on the week 5. So, first you have a random noise. Random noise is sampled from a Gaussian distribution. That means whatever the values that you are taking, these are the values which are sampled. Yeah, this is a hyperparameter. If you fix a latent size as 100, then you will take 100 such values from this Gaussian distribution and then pass that 100 values to a generator. Generator here is a neural network. When you say neural network, you will have parameters. Those parameters here are 5. These are learnable, trainable parameters. This generator takes Z and transforms this low level into an generated image. So, this generated image is to this generator you are passing Z and you are getting a generated image and you are calling it as X hat. This generated image size should be same as the data set, original data set size. Now, you can ask, how will we get to know? So, when you are coding, you will explicitly specify that towards the end you should get this particular size. Okay. Why is that we have to ensure it is same size? Because ultimately the generated image will be sent to a discriminator. So, when a discriminator, when you send it to a discriminator, if the size is not matching, it is a direct indication to a discriminator, right, that it is a generated image. Therefore, it will ensure that the size will remain the same. And second, one more reason why size has to be same is discriminator will see original images also. Original image will be of one size. Generated image, if it is of different size, how is that the network you have to design? Correct? So, because of that, both images should be of same size. Okay. I think up till here it is clear. Now, whatever the images that the generator has generated, which is this, is now passed to a discriminator. So, here the generated image is then passed to a discriminator. Discriminator is a neural network. If discriminator is a neural network, then that neural network will have certain parameters, and that parameters here is theta, that can be weights and bias. So, what is that input you are passing to a discriminator? The input that you are passing to a discriminator is this. Generated image is this, that is being passed to a discriminator, and here theta represents the parameters. Now, what discriminator will do? Discriminator will examine the generated image and say whether it is real or fake. Now, how is that it will give us, how it will tell whether it is real or fake? It is going to give us one probability, and that probability value will be always between 0 and 1. Okay. So, which means the discriminator is going to give us y hat. What is y hat here is the predicted value. What is that predicted value? Discriminator should tell whether it is a generated image or not. Discriminator has to tell that. So, y hat is the output that the discriminator is going to give us. So, that y hat is nothing but to this input, the generator is being generated input is being passed to discriminator, and discriminator is going to give us the probability. Now, suppose if the probability is 0.2, suppose if the discriminator has given this probability, what is the meaning of this? This means that the discriminator assigns only 20% probability that the generated image is real. In other words, discriminator, is it not, discriminator is very confident that image is generated or it is a fake image, right? So, this is how up till this particular step. I hope up till here it is clear to you. Generated image is being passed as an input to an discriminator, and the discriminator will take that generated one as an input, and it is going to give us the probability. Okay. Now, when it has predicted y hat, the next step is it has to calculate the loss, right? What is the loss here? Generator loss, which is denoted as LG. Now, if you have to calculate the loss, you need to have the ground truth also. You need to, if y hat is the output, you need to have y also, right? So, during a generator training, what we are discussing is the generator training. What is the ultimate aim of a generator? The generator wants the discriminator to classify the generated image as real. That is the ultimate aim. Whatever generator is generating an image, discriminator should classify it as real. If it has to classify it as a real, what should be the ground truth? The desired value y is 1. Y is 1. Just think carefully. Now, if a generator is generating an image, and for that image, if the discriminator is always giving a very low probability, which means discriminator is easily classifying the image as generated one. But ultimately, what is the role of a generator? It has to improve and then provide more realistic image. If it has to improve, its ground truth should be always 1. If the ground truth is 1, then if initially if it is giving the probability as 0.2, when you compare it with the ground truth 1, the loss is too much. When the loss is too much, is it not very good information is coming to a generator? If the ground truth is 0, suppose if the ground truth is 0, because if you are thinking that it is generated image, so y should be 0, then is it not this error will be very less when you compare with 0? When you compare it with 0, if the error is very less, ultimately what is that you are informing to a generator? That whatever image you are generating is good. Then where is that realistic image you are getting? I hope this is clear, right? So that is the reason why y is assumed to be 1. So this target is deliberately set to 1 because the objective of a generator is to fool the discriminator and it has to generate more realistic image. So I hope up till this point it is clear to you. So this is important. Before I go to the next slide, I am once again quickly revising. So there is an there is an noise. This noise is passed to a generator. Generator will generate an image. This generated image is passed to a discriminator, and the discriminator is going to give us the probability. And this probability is a predicted value y hat. This y hat should be compared with the ground truth, and that ground truth is 1. Then you are going to calculate the loss. Now, once this flow is clear, let me explain you the terms that are used here. So, this is generator parameter, generator network. The network will have parameters, so G phi. Now, for this, what is that you are passing? You are passing Z. What is Z? Noise. That is passed as an input. And what is that you get? From this, you get the image, generated image. Generated image is denoted as this. This is how you are denoting the generated image. Why? This is the one which is generating, and it is generating with the help of Z. So, this is the generated image, and we in short we are representing it as X hat. Now, you are passing it to a discriminator. Discriminator, it is a neural network which is having the parameters theta. Now, for this, what input you are passing? You are passing the generated image. What is generated image? Is it not this is the generated image? This is the generated image. That is passed as an input. So, when you pass this as an input to an discriminator, discriminator is going to give us the prediction. So, prediction is on this, right. So that predicted value is y hat. That is compared with the ground truth. Why ground truth is 1? That we have discussed already. Ultimately generator has to generate a realistic image. For the realistic image, y is taken as 1. Once this is done, you are computing the loss. So loss is between y hat and y. So once you compute loss, what is the next step? You have to backpropagate, and when you backpropagate, is it not you backpropagate like this? Ultimately you will reach to a generator. So rather than showing an arrow mark like this, I am showing a blue dotted arrow marks on the top. So here during backpropagation, what exactly is happening? Although you come through a discriminator, discriminator has the parameters theta, but you are not going to do any updations here. Gradients will pass through discriminator, but theta is not being updated, which means discriminator parameters are not being updated. Here the aim is generator. So discriminator will be made, freezed there. Then only generator parameters are updated. What are parameters? It is phi. So I hope generator flow is clear to you. This is important. Second, next let us look into what exactly is the generator loss. So go back and then think of binary cross entropy. So is it not binary cross entropy loss here? So now from this let us see how we will derive it to a generator loss. This is a simple binary cross entropy which we are seeing from many stages. We have seen this before also. Now here if you look into what is our ultimate aim, the aim here is during a generator training, the generator wants a discriminator's prediction for the generated image to become closer to 1. So which means whatever the images that the generator has generated, for that when you pass it to a discriminator, prediction should be closer to 1. That means if the prediction is closer to 1, what is the ideal meaning? Generator has generated a realistic image. That's the meaning of it. Yes. So that's what is the ultimate aim. During a generator training, the generator wants discriminator prediction, which means y hat should be closer to 1. Okay. If so that makes the discriminator classify all the generated images as real. Now, what is the target ground truth y that we are considering? Is it not y is 1? That we have seen some time back. Now you are clear why y is 1. Now just substitute y in the given formula, in the above formula. When y is 1, then 1 minus 1 becomes 0. This entire terms becomes 0. Then is it not when y is 1, this term becomes 0. Then you are left out with 1 into log y hat is minus log y hat. Is it not we are obtained with this? Left with this. Now what is y hat? Y hat is a predicted value. Prediction from where? Prediction from discriminator. What is the input that you have passed so that discriminator is predicting? Generated image. So is it not this is your y hat? So substitute that y hat into this LG, that is loss at an generator. So is it not this is the formula that you get? This is important concept. So generator loss is this. This is the generator loss. I hope this is clear to you how you have obtained. So you have obtained this because in our loss binary cross entropy, we are seeing that y is for a generator training, y is 1. When y is 1, substitute the formula value into the given loss function. So when the second term becomes 0, when the second term becomes 0, is it not we are left with only first term? And what is y hat? Y hat is the predicted value from a discriminator. How is that you are representing? It is discriminator by passing the generated data as the input. So therefore, loss function is this. I hope this is clear to you. Generator loss. So, what is the entire forward pass? We have a Z. Z is passed to an generator, and the generator is going to produce the generated image this, and that is passed to an discriminator d theta, and discriminator is going to give us the prediction y hat, and that later you are computing the loss. What is the loss here? The loss is this. This is the loss function of an generator. Now, let us say one example. Suppose if model has predicted y hat as 0.2. So, if 0.2, ultimate aim is it should be closer to 1, but what is that the model has predicted? The model has predicted it as 0.2. So, substitute the value in this minus log 0.2, is it not we are getting this? Is it not the loss is too much, loss is too high? When generated loss is high, what is the meaning? Two meanings. Discriminator is very successful in saying that it is a fake image, which means a generator has not generated a realistic image. Is it not these two informations is getting conveyed? Now, if this is the loss, during a back propagation, is it not this information is conveyed to a generator? When this information is conveyed, is it not generator will improve further? So, generator loss is high because the discriminator confidently identifies generated image as a fake. So, because of this, generator will get the information that I have not generated image properly. So, generator will improve. Next. Now, let us see what exactly is the back propagation. So, if you recall from our generator training, we have the overall, ultimately when you are back propagating, you should back propagate till the generator parameters. You have to update. So, what is the overall flow? Is it not from a loss? Loss you have obtained from x hat, y hat, that is a predicted value, and that y hat you have got from the generated data image, that generated we are calling it as x hat, and from there you are reaching it to an generator parameters of phi, right. This is the flow. During a back propagation, you are calculating the loss. From loss, you are reaching it to y hat. From y hat, you are getting it to x hat. From x hat to the parameters phi. So, is it not from loss, you first reach to an discriminator. From discriminator, you will reach to an generator parameters phi. In this, there are two important. What is y hat? Y hat is this. By now you should be very clear what is this notation, and x hat is a generated image, right. Now, just substitute the values. Now, you are back propagating it. Back propagating is always a chain rule. Using a chain rule, can I write derivative of loss with respect to 5 is, first you will reach to this derivative of loss with respect to y hat. From y hat you will reach to x hat, derivative of y hat with respect to x hat, and from x hat you will reach to the parameters phi. Using the chain rule, can we write in this way? Yes. Now, at the right side you have the values, you have what is y hat, you have what is x hat. Can you just substitute those values into this formula? In this y hat, can you bring this value? At this x hat, can you bring this value? Is it not? It looks something like this. Substituting the definitions, derivative of loss with respect to phi, is it not you have reached to this point? So, all of these are easily differentiable. So, therefore, we have got this value. Now, you have to finally update the generator parameters. So, what is that you have to update? Those parameters of phi. So, 5 new is 5 old minus learning rate, derivative of loss with respect to the parameters. So, is it not this? So, in this learning, this is the learning rate. Now, is it not you have easily updated the parameters during the back propagation, you were easily able to update the parameters. Now, in this formula, you look very carefully, we have even theta also, we have discriminator theta. So, during a back propagation, during this particular step, or when you are training the generator, when you are back propagating, although there is a discriminator theta, theta is frozen. which means there is nothing that you will be doing here. So only the 5 is updated, that is generator parameters have been updated. Now by updating these parameters, what is your ultimate aim? What is the purpose of update? The purpose of this update is to modify the generator. Why you want to modify the generator? So that a discriminator assigns the high probability. If it is assigned high probability, then is it not generator is very good? Then a discriminator is not able to identify which is real or which is a fake one. So the purpose of this update is to modify the generator so that discriminator assigns the high probability of being real to a generated image. So which means this value should be closer to 1. When this value is closer to 1, there are two meanings again. Discriminator is not able to identify whether it is real or fake. If discriminator is not able to identify, which means generated images are very much closer to the original one. So the discriminator is definitely used to compute the gradients, but its parameters remain fixed during the generator update. So this is the overall meaning of an overall working of an generator. So during this particular phase, only generator parameters have been updated. How is that generator parameters are updated? Is it not we are getting loss? From that loss you are going back to an generator and you are updating the parameters. In this process, discriminator parameters remain fixed. Okay. So with this we have finished the generator part. Now let us look into what exactly is a discriminator. Now so far we have clearly understood the generator, its loss function and its backpropagation. All of that is been made clear. Now let us look into a discriminator training. So the second network here is discriminator. When you look into, there are discriminator is the one here which will receive two types of inputs. Here it is receiving one from here, one from here. There are two types of inputs. One are the real images. Second one is the generated image. So and what is the task? The task is to correctly distinguish between them. So now we are only discussing about the discriminator. At the discriminator, let us look into the first path, and the first path here is real image branch. We are looking into this part now. We are looking into this. So real image branch. Okay. We first take a real image X from the training data set. Let us assume this is the training data set. We take real image X from the training data set. Mathematically, we write it as this way. X is sampled from this particular distribution. What is this P data of X? It is the underlying distribution of the original data set or the real data set. Don't get confused, just because we have written this, we are not learning any of this probability. No, it is X is been sampled, X is taken from this particular distribution. Okay, this means X is a sample which is drawn from a real data distribution. That's the meaning of this particular line. In practice, we simply select a real image or a mini batch of real images from an available training data set. We simply take this data, and these real images we are denoting it as X. That is passed to a discriminator. What is discriminator? Discriminator is this. So when you pass it to an discriminator, discriminator is going to give us the probability for this particular one. So when it gives the probability, what should be the probability? What is the role of a discriminator? It should clearly tell it is real, and it should clearly tell it is fake. So which means when a real image X is passed to an discriminator, discriminator should assign very high probability to d theta of X, right? So can I say y hat is prediction made for real image, right? So that is what is y real, which is d theta of X, and this value should be very high. This value represents discriminator's estimated probability that the input image is real. Now, when Now look at this. When y hat is the prediction made for a real image, what should be its ground truth? What should be y real? The y real, the desired target is y real should be 1. Why y real should be 1? Because it's a real image, right? When it is a real image, the prediction made by the model should be very high and its ground truth should be 1. I hope this is clear. Therefore, for a real image, the discriminator should produce this d theta of x a value which is closer to 1. I hope this is clear. Suppose I have taken one real image x and that real image x is passed to a discriminator, and discriminator is giving the probability 0.9, which means discriminator assigns 90% probability that the image is real. So, which means it is a good prediction, right. So, okay, let us assume we have reached up till this point. Now, is this steps clear? You have taken a real image, that real image is passed to a discriminator, discriminator is giving us the prediction, and that prediction we call it as y real, y hat real, and that prediction should be closer to 1. When that prediction is closer to 1, which means for a real image the model should assign high probability. If that is the case, what should be its ground truth? Its ground truth should be equivalent to 1. Okay. Now, let us try to understand what exactly is the second path. Second path is about the generated one. So, some time back we have already seen in detail what exactly. So, I will be little fast here. We sample Z, that is a random noise vector, and that is sampled from a prior distribution, that is Gaussian distribution. This noise vector is passed through a generator. So, it is this, and it produces an generated image. So, can we call it as generated image fake, which is nothing but this. Okay. Now, the generated image has the same dimension as the real image. So, it can be passed through a same discriminator, because discriminator you do not have two discriminators, it is only one discriminator. Discriminator is being designed based on the real image dimension. Now, if you have different dimension, then how can you pass it to that same discriminator? Therefore, the generated image has the same dimension as the real image, so that it can be passed through a same discriminator. Okay. Now, the generated image, this is what is the generated image, that is given to an discriminator d theta. It is given to an. So, what is that discriminator will now do? Discriminator produces another probability. What is that another probability? Y fake and hat, y hat fake. This value is again interpreted as the probability that the input image is real, right. Now, here this is the image prediction made by the model. Now, if this what should be this value? This value should be closer to 0, which means the value will be should be less. Now, if this value should be less, what should be its correct target, or what should be its ground truth? The ground truth should be equivalent to 0. Now, do not get confused, earlier we said it as 1, but that is for a generator, but here it is a discriminator. For a discriminator, when you are passing the generated images for a discriminator, when you pass the generated image, then its target value should be closer to 0. Therefore, y fake value here is closer to 0. Now, if the y fake value is closer to 0, which means the discriminator should therefore produce this value closer to 0. For example, suppose if the value given by this is 0.2, which means the discriminator assigns only 20% probability that the generated image is real. If the generated image is real, if it is assigning only 20%, which means it has correctly considered that the image is fake image, right? Okay. This is all with respect to we have reached to this step. I am repeating the second branch. First you are taking the noise is passed to an generator is generating an image, and that generated image is passed to an discriminator, and discriminator is taking the generated image and it should assign the probability. Because it is a generated image, for a discriminator this value should be low. If this value is low, it should be closer to 0. Therefore, its target y should be 0, right. So, this is for fake and this is for fake. For a real image, let us take real image x, when that is passed to an discriminator, and discriminator is has to give us the prediction, and this prediction should be high and should be closer to 1. Why closer to 1? It is a real image. If that is the case, its ground truth should be closer to 1, and this is all for a real image. I hope these two are clear to us. Once this is done, you have to now compute the loss. We are computing the loss here for the first path, and for the generated path we are computing the loss. Once you compute the loss, you will combine both these two losses, LD, that is loss at a discriminator will be real loss and a fake loss. Then you will backpropagate it. When you are backpropagating, till where you will backpropagate? You will backpropagate only till discriminator, and you will update those parameters. Now, I hope up till here it is clear to you. Let us now discuss in detail about the loss. Look at this. Again we are considering an binary cross entropy, which is y log y hat plus 1 minus y log 1 minus y hat. This is a binary cross entropy loss. So, once you take this, you remember there are two things, one is real, other one is fake. So, let us now look at the real one. When it is at the real, what should be y real? The ground truth should be equivalent to 1. If it is equivalent to 1, just go back to the formula and then substitute. When this is 1, 1 minus 1 becomes 0. So, you will be when this becomes 0, this entire term is not there. When this entire term is not there, we are left out with minus 1 into log y hat. We are left with only that, right. Now, when we are only left with this, we have y hat. What is y hat? Y hat is a predicted value. What is this predicted? Is it not you are passing the original image? So, the d theta of x. So, it is minus log of x. This is what is the loss, and the loss at what? Loss for a real images. So, some time back we have seen we are now calculating this part. So, this is the real, L real is what we are calculating. So, I hope this is clear to you how we got the loss term for the real images. Y real, whatever the model has predicted is d theta of x, and for original y real is 1, y hat is d theta of x, y real is 1. Just to go back to the formula and substitute. When y is 1, then 1 minus 1 becomes 0, this entire term becomes 0. Then you are left out with only this term. You are left out with this term. So, what is y hat? Y hat is d theta of x, and this is for real images. So, y real. So, and what you have obtained is L real loss. This is the loss function, loss formula what we have obtained. This is the first. Second, you have generated also. How is that you will be writing for generated? So, go back for a generated, what should be the original y fake one? The original y should be 0. So, when this is 0, if you consider this term will not exist, because y is 0, 0 into something becomes, and 1 minus 0 will be 1 log. We have 1 minus y hat, right. Now, what is y hat? Y hat is the prediction made by the discriminator for a generated images, prediction made by the discriminator for a generated image, right. So, this is y hat, and it is for a fake images, right. So, this is what you see, generated image is this, and y hat fake is the prediction made by the discriminator for the generated image, and for this the ground truth is 0. So, the first term becomes 0 and the second term is 1 into this predicted value, and predicted value here is this. So, this is what is the overall loss function for an generated images for a discriminator. I hope this is clear. Once the terms are clear, it is very simple. It looks very complicated math, but it is very simple. What is the total discriminator loss? Recall from the image, you have one loss from coming from the real images, one loss coming from the generated image, and the total loss is the addition of L real and L fake. So, this is what is the total loss, and just some time back we have seen what is the L real, this is the formula, what is L fake, this is the formula. Just substitute back into this. So, is it not L real is this and L fake is this? Take out the minus term common. When you take the minus term out, then you have this entire. So, this is the total discriminator loss. So, once you have a discriminator loss, the next step is you will be computing the gradients. So, I hope up till this step it is clear to you. Yeah, I hope every math is clear here. What is the next step? It is an backpropagation. Now, when you look into the diagram, backpropagation is only up till the discriminator, which means generator is not at all getting involved, which means those parameters are frozen. What 5 parameters, generator parameters are frozen. So, using a chain rule, the backpropagation is all about you have to compute the gradients. So, using a chain rule, if this is the loss, then the chain rule says derivative of loss with respect to theta. Why theta? Because you have to update the discriminator parameters. Discriminator parameters are theta. So, the derivative of loss with respect to theta, derivative of loss fake with respect to theta. So, which means now you should compute this and you should compute this. So, the gradients has to flow back. From where it will flow back? The total loss LD. From there you will come to discriminator parameters. So, the path is very short here. So, because of this, although you have L fake which is generated images from the generator, but during a discriminator training 5 is frozen. Therefore, the gradients are not used to update the generator parameters. You are only going till discriminator and okay. Now, let us see what exactly is these two terms. Once we know these two terms, then updating theta becomes easy. Now, just recall from that diagram, how is that you will be, first you have to calculate this. If you have to calculate derivative of loss with respect to theta, what is that path? Is it not this is the path? You have a theta discriminator. Discriminator has predicted this. From there you have calculated L real, that is loss for a real parameters, real image. If this is the case, using chain rule, can I write in this way? So, L real, derivative of L real with respect to theta, can I write it as from L real, from loss you will reach to this, from here you will be reaching to this parameters theta, can we write? So, derivative of loss with respect to theta is derivative of loss with respect to its predicted value y hat and y hat with respect to theta. Now, what is y hat real? That is a prediction made for a real images. Who makes the prediction? The discriminator. On what it will predict? On real images x. So, therefore, you have substituted y hat real as d theta of x. You have substituted, which means each of these values can be easily computed. right. So, I hope this is clear. The path you have to update these, you have to get these two values. Loss with respect to real images is, you will be getting its a prediction y real. From y real you can reach to a discriminator parameters. Y real images also it should able to predict properly, and for fake images also it should able to predict. So, you are able to reach to parameters and you are updating here. Second, what is for a fake one? For a fake you get L fake, that is loss for a fake images. From there you will reach to y hat fake, that is the prediction made by the discriminator model on generated images, and then you will reach to a discriminator theta. So, is it not this is the path? So, can you able to write using a chain rule? So, L fake with respect to y fake and y fake with respect to theta. So, what is y fake? It is the prediction made by the discriminator on the generated image. So, this is, so you have substituted those two values. By substituting those values, you have got a derivative of loss with respect to theta parameters, and for a generated image. What is the total loss? The total loss here is L real plus L fake. So, this we have obtained, and this we have obtained. Just substitute the values, add these, we are going to get a derivative of L with respect to theta. So, once we get, is it not, you can update as theta new is a theta old minus a learning rate, derivative of LD with respect to theta. So, where this is a learning rate, and during this discriminator training, theta is updated, but 5 is frozen, right. So, this is all with respect to an discriminator training. Although it looks very complicated, but understand the terms thoroughly and then understand the chain rule, you can able to do it very easily. Now, let us see one numerical example, and we are dealing it with the discriminator. Suppose we have LD of x, that is the prediction made by the discriminator on real image is 0.2. The prediction made by the discriminator on generated image is 0.2. So, is it not very good prediction? On real image it is giving 0.9, closer to 1. So, which means real image is treated as real, predicted it as real. So, good. Second one 0.2 is on the generated image, what is the discriminator prediction? 0.2, which is closer to 0, which means both these are very good. If both are good, which means discriminator is very good, ideally discriminator loss should reduce. So, let us see that. So, what is the loss from this? The loss is very less. So, why loss is very less? Because it is predicted very well. So, then take this and then compute the loss. So, the loss is once again very less. So, compute total loss. What is the total loss? Addition of these two. So, overall discriminator loss has reduced here, is low. Why it is low? Because for a real image it has assigned high probability, for a generated image it has assigned low probability. So, therefore, it is overall it is a very good model. Now, let us take an counter example. Let us take while generated image is assigned low probability. So, overall the model has done well. So, let us now look at an other side. What is the meaning of this alone? This is a discriminator which has predicted on a real image. So, the value is 0.2. So, prediction made on real image, if the value is low, what is the meaning of it? For a real image, the model is giving less prediction, which means discriminator is not doing good. So, this means a discriminator assigns only 20% probability that real image is real. How? For a real image it has to give more probability, but it has given less. Okay. Now, let us look into this. What is the meaning of this? This is the discriminator has predicted the prediction on the generated image, and it is 0.8. On the generated image, discriminator has given high probability. So, ideally that value should be closer to 0, but here the value is closer to 1, 0.8. Model is not doing good. Discriminator, which means a discriminator has assigned 80% probability that generated image is real. Very bad discriminator. What is the total loss? I mean, loss on real image. The loss on real image is very high, 1.609, and the loss on generated image is also very high. So once the loss is high, then what is the total loss? The total loss is also going very high. When the total loss is high, then during a backpropagation, what is that information you are conveying to a discriminator? You are not doing good. If you are not doing good, is it not discriminator becomes more active and then try to learn it more carefully? That real images should have a probability 1 and generated images should have a probability closer to 0, right? So this is all the overall working mechanism, and I request you to take a pen and paper when you are learning this particular one. So in this particular session, this is very important session where you have seen the basic working mechanism of GAN in a more detailed way, and in next coming session we will be looking into the GAN objective and then the loss function, where we will look into the training procedure and then how GAN will converge, and we will look into one of the important concept called Nash equilibrium. This will be the point of discussion for the next session. Thank you.